open time server and time card, but before that I will just give you quickly a background, let's say, about Meta and our global footprint. This map is like all I was able to find basically to show the latest, and I couldn't find, like, let's say, something updated with our large footprint, but this is not just data centers, this includes also colos and some other things. And this map was like more tailored to renewable energies and like basically what we use to power these things. But overall, for those who are not familiar with like the scale, we have like these data centers which they look like an H on top, and then they're basically these two data halls, and in the middle is basically the office space. And in every one of them you have basically these rows of racks, and you have these rooms for every one of these halls called info. And that is where emitter basically gets aggregated minimum point of entry. And that's like where it goes on the terrestrial cable and so on. And this is where we decided to put basically these time appliances. So now going back on the background, it was a unique problem to deal with. Again, thanks to the adoption that telco had for PTP. I mean, it made the technology have like a strong application, and perhaps that's the reason why we have it even around. Everything on the downside, everything was basically tailored for telco. For example, in telco, you don't need to have, let's say, 1 million units in Unicast and like you name it. So for data center, you have these shallow, basically hierarchies, but really they become fat, wide. Like you have, let's say, 5, 6 hops, and then all of a sudden you have 1 million nodes. So you have to also only use Unicast, like multicast, like a taboo to bring up there, because it makes sense. Let's say if you want to go multicast, and all of a sudden you have like 1 million different like nodes like receiving some packet that is irrelevant to them. Also, with this BGP algorithm, you have a hard time altering the throughput of packets in the fabric of the networks, meaning any packet coming in should also get out. You cannot terminate packet inside, or you cannot generate new packets from inside and then have different packets coming out. So therefore, boundary clock has no chance pretty much in the data plane. So therefore, transparent clock only. And also, because of the sensitivity of the data and so on the data plane, you can really not afford any third-party equipment sitting there, closed source, I don't know, you name it, and have data packets. That's like pretty much like the most important thing for data centers to go around, because you definitely will have like a point of vulnerability. You can take a packet and send it out with different mechanisms. So therefore, you can't really have anything third party sitting there. And everything has to be pretty much provisioned, maintained by the entire data center, as the other servers pretty much get provisioned and so on. And also, you need to have transparency and easy access, meaning like everything on the data plane should not have like, let's say, some weird, let's say, web interface, I don't know, smart interface, whatever. You have to have everything like very clean, like with pretty much similar to every other equipment, every other service that sits there, so you can simply run like a batch script, and then you have 7 million, I don't know, whatever million machines like right away getting like, let's say, a configuration. And traceability. And traceability here is more of, if you have boundary clocks, you have no idea how pretty much like the clock, like the synchronization happened to that boundary clock. And like, let's say you have layers of boundary clocks, in the end you have any like insight of like how is basically the accumulation of the error as you go through. So this all pretty much led to the need for scalability, and that was like one reason also we looked into open sourcing everything that we're working on. My obsession with open source is nothing I can hide, but the main reason for that is you need to have a lot of people working on something to make it really cool. Like you can see this, you can see Linux versus Windows, like, or like many more things, you know. So, and also you want to have like a feature-rich product. Like you want to have, like you don't want to have any restriction. You don't want to be at the mercy of small vendor, big vendor. Hey, please, can you add this? Oh, what's your quantity? I don't know. Like again, the nature also of these time appliances is pretty interesting. Like you have, let's say, a data center at scale of, let's say, Meta, and you need, I don't know, maximum maybe 500 of these units with, I don't know, so much redundancy, because that is how these equipment like are pretty much sitting. They're sitting on the top of a hierarchy. They're not sitting at scale for all the servers. You need, like effectively, you need one of these time servers to pretty much serve an entire data hall, if not like an entire region. But then you add like this redundancy and other things and so on. Also, flexibility, let's say you change from 10 gig, you go to 100 gig, now from QSFP go to 200, 400, 800. Again, you can't be at the mercy of vendors to like decide for you like what we have and so on. So you have to have some freedom there, adaptability, versatility, all of these things, they all come in place when you want to, let's say, address problems at this scale. So this is what pretty much OpenTime Server came in. And again, OpenTime Server came for like based on the need that we had in the data center. And also we needed to have like certain like things like state of the art. Like for example, how you do the communication, like again, IPv6, you have to have, let's say, these miniaturized atomic clocks. Again, thanks to all those who pretty much made these technologies possible. Otherwise, this couldn't have been happening. Like, put an atomic clock on a PCIe card, and I take your word, Judy. Like, we're looking for better technologies like optical clocks sitting on a PCIe card. So there will be perhaps time card 3, 4. You made it. So again, as I said, like we pretty much said, okay, time appliance, create this box, and we want to open it up, and now we have this piece and also open source and everything else, the software stack, everything like pretty much like flexible and allowing the customer pretty much use what they want. So what we did in terms of separation is like we use this analogy again. Past life, I used to be super enthusiastic about space. We thought of it more like you have the rocket, and time card is just a payload. You can put NTP, PTP, White Rabbit. I want to put PPS here, but I thought it's an insult to put PPS with these other ones. But I believe in PPS, so PPS is my currency. So, and time card is basically just providing the payload, and then you can take it from there and like any relevant method. You can even have, I would say, none. I should have added also to that list, where you just have that unit and you want to have precision time there, or let's say it can be the end users. Like that's the vision I have. Like I want to have every computer in the world to be in sync, like single digit, 2-digit nanosecond, whatever is going to be possible. And how we look at different domains of this precision time is like, because I always get this question, so we have time card and we don't need PTP. No. Time card, of course, I mean, if money was not a problem, and I think it's also a stupid like solution, is like you put time card on every server. So you don't do that. You put time cards for between data centers. In a data center, you go with PTP, and I wish Kevin was here. Then inside a server, you go with PTM. And PTM is like precision time measurement, where again, that last foot of synchronization, where now all the peripherals in the server will get in sync. Like you take the sync now from the NIC, and then you give it to this. Like you have a projection of the always running timer of the CPU, and then from there you can go to the GPU. You can do a lot of things. And PTM on its own is actually a very interesting thing. When you look at all this, again, this is what I have to deal with the NICs. Most of these NICs are, again, thanks to the telecom industry, they're designed to, like, again, the server, whatever, the software stack tries to do the synchronization. Then you get the NIC providing you a pulse per second, and the pulse per second there gets used in that, like, hardware for the radio and everything else, but it's not really consumed at that precision in the OS, in the software. In Datacom, it's very interesting. We got these NICs, and they don't even have, like in the beginning, they didn't even have this PPS and signal and everything else, and they were saying that, well, you're not going to use it, so we basically take it off. But you have hardware timestamp, you have PTP support, and so on. But what can we do with it when, like, you bring all this, like, let's say, nanosecond precision to the NIC, but then you get into the OS and you're back at, like, let's say, tens of microseconds. And that is where basically PTM came in. And PTM, again, I wish Kevin Stanton from Intel was here. He would have perhaps talked about it, where now with PTM, and any CPU newer than, let's say, 2021 is capable to do PTM on the consumer side, 11, 12, 13, and the new Sapphire Rapid, they can do PTM. They get you down to 2 nanosecond granularity, and then from there, the sky's the limit. You can do a lot of things. So, just a little bit of history about time card. This was the first time card, again, a lot of junk from eBay putting together, and we're like, okay, it's possible with a Supermicro server. And then it became a little bit cleaner, and then it became this sketch that I put together, and slowly evolved. Like, here I put everything. I put like an OCXO, TCXO, an RTC even. Like, because I was like, let's check if everything, because it's 1970s something you get really obsessed with when you turn things on and GPS is not working. So it was even an RTC there, and we tried to basically figure things out. I was super excited about the CSAC, again, thanks to Robert Dutwak. And then, again, settled, SA53 is going up, so we get back to this. And again, this was like time card 1. And from concept to first prototype, and industry adoption was within 2 years. And time card 2 came in, and this idea, again, credit to Microchip, that was mainly because SA53 had 2 PPS inputs. And I started thinking like, oh, now I can do, let's say, 2 sources, one like different band, different technology. Let's go, let's say, with 5G, let's go with Citella has like some amazing technology. The technology keeps like going up, like Septentrio. I really practice to pronounce that right. It's so hard. And you can just add all of them together. You use your atomic clock to, let's say, calculate some ADEV, whatever, some criteria to see which one you should select, and you pick that one, use that one for discipline. Or you can discipline both at the same time. One goes real time, one goes free running. So a lot of options. Again, time card 2 is allowing us to do most of these things. But main things are support for PTM. So now we can basically stick a time card in a system remote, and then you can get pretty much that precision time all the way to the CPU. And then from there, you can have your GPU also in sync. Again, that's not possible yet, working on it. And also we added MSIX instead of MSI. So the resources, like the interrupt resources are not just getting exhausted, because there are a lot of interrupt resources on the card. Like there are multiple serial ports, and like the time card simulates anemia generated by the atomic clock, a lot of things. And also, thanks to, again, community. See, this is where community comes in. Like if you look at the placement, we had the Mac sitting on the right, and and with someone like did some FEA analysis, and like basically what Will from Microchip was telling us, that On this axis, you have like some sensitivity on this one because you have the laser versus the vapor chamber and so on. So then we did some, again, refinement of the placement to have, let's say, minimum effect on vibration. And these are just fine tuning. And then we added also IRIC B. Again, the IRIC B is not encoded, so you have to add another circuit to put it on top of a 1 kilohertz carrier. TCF77 and also WWDB, they're all in the core. You just enable them. You can use them both input and output. And then we start looking into other GNSS receivers also supporting them, because we used to have only the U-blocks messages, the time and time LS, but then we added the one from Trimble's new company. So hard that one. So the name.
ProTempus.
Which one?
ProTempus.
Thank you. Yes. I think the practice for September took all the neurons off. And we also tried Furuno, and we just want to add like everything else. But guys, please sit down and come up with like some extension of anemia, so we don't need to have for everyone like these special messages. Please. Also, we added like frequency generator, frequency counter, all of these things. And again, everything we try to put open source. And here, again, my obsession with these CSACs. Now I see like this low noise CSAC, so we added that there. And then also on the GNSS with the receiver, we started developing a SDR-based one, based on the NXT LA9310. I wish Wim was here. And also we put a larger FPGA now from 100, we went for the 200. Block diagram, now everything is open source, literally everything is open source. You can get like the FPGA project from GitHub and you can modify it, do whatever you want with it. The PTM is still not implemented there. That's mainly because the AXI PCI interface doesn't support it, so we are shifting from the AXI bridge basically to a light X, and on the light X we're trying to add the PTM support. And again, there are different functionalities and so on. And then the memory map is again something that we're trying to push to every other derivatives for this card, different companies, to have interoperability. And the driver also the same thing, like we made it extremely simple, like you basically use this sys tree where you have a bunch of files, you can echo from them, you can echo to them, or you can read them, and then you can control pretty much everything in a time card. Like you have the serial ports, you have the SMA connectors, you can control them. If you forget like what things you can do, you go all the way to you look at like what are the SMA input or output options. Every SMA connector can become input or output. That was also an interesting thing, because we had, like, for example, an application which some software people, they wanted to time different parts of, let's say, their code. And we had another application that someone needed 4 timestamps. So 4 inputs versus 4 outputs. And also, this is the main one. Again, this is what distinguishes time card from everything else. There's a POSIX clock that you can pretty much copy it to your NIC, and then you have, like, let's say, the time dissemination network. Again, open source, you can find it on timingcard.com. And we have also this IEEE, this new PAR. Dennis is here, I wish Kang was here. 3335, I'd like to, so 3333, I got 3335 easy. I wanted IEEE 3331, but it didn't happen. How many are 3335, still not bad, so. And again, we had our kickoff meeting, and we'd love to have you guys give your inputs and join us. Yeah. We also standardized this, the RCB form factor, and the oscillator carrier board. And coming up, probably we'll have also miniaturization in this, and thank you very much.